Hi, my name is Jensen Joshua Lim, and this is Physics 2211, Lab 2. The purpose of this lab is to understand the motion of a falling object and the forces acting on the object, such as drag and gravitational force. Another thing is to produce a computational model to compare the motion of the object, one with drag and one without drag, and we hope to be able to explain terminal velocity. By the end of the lab, we will expect the computational model with both gravitational force and drag force to be more accurate than the gravitational force by itself. The few important concepts that we'll be looking at in this lab will be Newton's second law. So as we can see the equation F equals to ma, where it states that the force is equivalent to the mass times by the acceleration of the object. Another equation we can see is F net equals to the change of momentum divided by the change in time. And another one that we'll be taking another look at will be terminal velocity, which is indicated by the blue picture at the bottom. Here are also more important formulas that we'll be using throughout this experiment, which includes the velocity update formula, position update formula, as well as the drag force formula, which is negative b, which is a constant, times by the velocity squared times by velocity hat. So the experiment that we'll be doing today would be capturing the motion of a falling paper ball while using Tracker to analyze the video. So once the ball is dropping, I'll be using Tracker to analyze frame by frame of its position. And from there, we can extract the position and time data from Tracker to plot a velocity time graph. And from there, we'll be able to determine whether or not it has drag or without drag. So in this experiment, the system will be the paper ball itself, whereas the surroundings will be gravity and the drag force, or better known as air resistance. So the important things to note for this experiment is the initial conditions. So you can see that the initial position of the ball starts at 0, 1, 0, which is 1 meters in the y direction, and the initial velocity starts at 0, whereas the mass of the ball will be 4.5 grams, the Earth's gravitational force will be 9.8, and the j hat, which is the direction of the ball, will be 0, 1, 0. And if you take a look at the graph, you could see that the position will gradually increase at a steady speed, and then it stays at a constant velocity, and then it slowly decreases towards the end. So the code on the left would be the code for only gravitational force acting on the paper ball. And as you can see that the formula that we'll be using will be the velocity update formula. And since this is a constant force, we have to use the average velocity formula, where you take the initial velocity plus the final velocity divided by 2. And after that, you plug in that value into the position update formula, where you get all your position data at a certain time interval. As you can see here, this is the position time graph for only the gravitational force acting on the ball, and you can see the shape of the graph is parabolic. So on this graph, you could see the comparison between the observed data versus the computational data. And from here, you can see that the computational data shows that the ball travels faster than the observed ball. So this is the code for the gravitational force with the drag force. Overall, the code is pretty similar. It's just that you'll be including a new equation, which is the drag force equation. So this is the position time graph for the gravitational and drag force. And you can see the shape is pretty similar as well, which is a parabolic shape. So you can see the graph is pretty similar to the previous one, where the computational data shows that the ball dropped faster than the observed ball. So if you compare all three together, you could see that the ball that's experiencing drag will travel at a lesser distance compared to the one without drag. So from here, we can conclude that the gravitational force and the drag force model is more accurate when predicting the observed motion. But some errors may include the distance measured may be too short for the experiment, and therefore it can be improved by repeating the experiment and finding the average position at each time interval. So some discussion questions include whether or not we could predict a terminal velocity based on our velocity time graph. So the velocity versus time graph will indicate a continuous acceleration of the atom due to the gravity without drag. The atom is subject to zero net force at terminal velocity, which means when the drag force is pushing the upward force precisely equals the force of gravity by which drags the object downwards, which overall balances the result. Another discussion question includes whether or not the terminal velocity will be affected if the initial velocity of the object was non-zero, meaning it will be thrown downwards. Well, if the initial downward velocity in this case is non-zero, that means the motion dynamics will be affected. This also means that the non-zero initial velocity would lead to a distinct acceleration phase. Therefore, your terminal velocity may differ as it is influenced by the initial velocity.